So hello everyone. Today I'm going to talk about categorified cylinder tangle invariants via quantum symmetric pairs. So yeah, let's go. Before we start, I would like to give you a brief overview. This whole story on the right column will be parallel to the reciprocating to if invariants, and in the decategorified world, this is just taking the quantum group UQGLN module, and this is a Schroeder dual to type A Hacker algebra, and therefore you can have a description of endomorphism rings of the representations. And here, what we do is that we consider the wedge powers of the natural representations of the quantum GLN, and the tensor products of these representations. Their endomorphism rings are controlled by a certain web category, which I'm gonna talk about in a minute. And then if you categorify this, you will use translation functors for the Lie algebra GLN, which will categorify the representation intertwiners. And in the case of n equal 2, you just recover the Hovanov homology. And today, what I'm gonna talk about will be the cylinder tangle invariants. And instead of the quantum group, I consider this co-ideal subalgebra modules, which are actually, I just take, this co-ideal subalgebra is Schroeder dual to the B algebra, and I just take the wedge powers of natural representations of this quantum group UQ of GL2, and yeah, in general, the representation theory is too complicated, so I just ignore that. And if you want to categorify this, you consider translation functors for SO2, and we also expect a new Hovanov type homology for this story. Okay. So I would like to mention a few important results from the representation theory side. So from the 90s to 2015, the theory of quantum symmetric pairs were developed. I mean, they were defined by Lester and then developed by these people. And Kolb generalized these to alpha and Casimudi case. And Balagovich and Kolb had some also structure theory on these algebras. And around 2013, the intertwiners, so the morphisms between these representations were described by Bao and Wang via Schroeder duality, and also by Erich and Stropper via School-Hall duality. And in their paper, they also described the intertwiners together with they just categorified the intertwiners and the co-ideal action. Okay, so this co-ideal subalgebra, which also appeared in the previous talk, is generated by these elements inside the UQ of GL2. And yeah, basically what you do is that you just put this F1 and put it together with B minus 1 up to some case. And this picture shows you the natural representation of the quantum symmetric pair, and also the quantum group. And I would like to remind you about the web category of type A, which describes the quantum group representations. So this is a CQ linear, the additive closure of the CQ linear strict monoidal category, whose objects are just sequences of natural numbers, and morphisms are generated by these trivalent graphs. And the relations can be found in Sartori, Tubbenhauer, or Kautis, Kamnitzer, and Morrison. So our approach to the co-ideal web category would be that I describe them via generators and relations, and the generators are just one dot on a single strand, and I define them to be the right module category over the type A web category, because this is a co-ideal, this is not a Hopf algebra, and this module category just means that I put my trivial graphs on the right-hand side of my dot, and I'm not allowed to put them on the left-hand side. And I'm gonna just show you some relations. So if I do my dot twice, there will be just the identity, and and this dot on the leftmost strand interacts with this crossing of the first and second strand via the type B grade relation. This is just from the Schroeder duality, and the proposition is that I have full functor from the type B web category to the representation category of the co-ideal subalgebra by restricting the quantum group representations. Yeah, and this just provides a new diagrammatic interpretation of the quantum school duality of Ehrlich and Stopper. So I would like to show you one particular element, kernel element of this representation. Namely, if I do my bubble but add a dot in the middle, then I just get 0. So I also have a nice diagrammatic basis for the web category, which is just splitting all the strands into ones. And in the middle, I just do my type B hacker algebra. So the basis elements will be just parameterized by the double coset representatives of type B web group. So our main theorem today will be just a tangle invariant in the solid torus. So namely, if I have these wrapping around the pole thing, I just send them to the dot up to a scalar. And the claim is that this is an invariant for cylinder tangles. So let's just compute some examples. If I just close up this generator here, what I get is just 0. It doesn't see the wrapping around the pole thing. If I make it slightly more complicated, what I get is still 0. But fortunately, if I close up a type D braid, then I get something which is non-zero. And now I'm working on the categorification of this invariant. And the idea is that I consider the Lie algebra SO2 and I consider this type A parabolic subalgebra. And in there, the simple representations are just labeled by the same combinatorial data as in the type A case. But this extra reflection gives me just several copies of this type A parabolic category O. And there I have these translation functors on and out of the wall, and hopefully they will categorify my dot. Conceptually, this is already done in Ehrlich on the Stropper, but I just want to make it more explicit. So this approach I described is basically a Lie theoretic generalization of the Lie theoretic Hovanov homology. But one can also ask, what if one does the type B or D arc algebras, and maybe there will be something similar to Hovanov homology. Yeah, that's all I have to say today. Thank you.